Hello. Today we want to do some applications on the basic algebra of sectoral structures. We'll do a few simple examples just to see how we can apply them. We're going to begin with this notation, an to the power of 2 dot. So here we're saying an squared, but as a dot product, so that we can distinguish between the direct or homogeneous or dot product and the polynomial product. So we'll say an squared dot is equal to 941 subscript 14. What is an? Very simple. We just take the square root of each of these terms. In which case this will give us 321 subscript 6. If any of these numbers did not have a natural square root, then there will be no solution in sectoral structures. Let's say 3an plus 212 subscript 5 equals 545 subscript 14. This is really just like matrix addition, so it's very straightforward. We will say 3an is equal to, we subtract each of these from the other sectoral structure. So this will be 5 minus 2 is 3, 4 minus 1 is 3, 3. So 333 subscript 9. And then an would be, we divide each of these terms by 3, an would be 1 cubed subscript 3. Now let's do an example using the polynomial product. So we will say an squared, and we'll put a times next to the 2 instead of a dot. So an squared equals to 4 squared 1 subscript 9. So this means that an of x squared is equal to 4x squared plus 4x plus 1. We factor this, we get 2x plus 1 squared. Therefore, an of x is equal to 2x plus 1, and an is equal to 2, 1 subscript 3. Now here we have an example looking at two sectoral structures and using both types of multiplication. So an dot bm equals to 6, 1 subscript 7, and an times bm equals to 6, 7, 1 subscript 14. So let's begin with the dot product. The dot product, keep in mind, is a homogeneous product. So since this result has an order of 2, then we know that both an and bm must have orders of 2. So we need natural numbers that give us a product of 6. That will be 6 and 1 or 3 and 2. So we can find out the first part of the result. It will either be 6 and 1 or 3 and 2. And then the second part is going to have a product of 1, so it must be 1 times 1. So therefore, the answer is one of these two sets, either 6, 1 and 1, 1, or 3, 1 and 2, 1. To be sure which of these is the answer we want in this system of equations. Now, if this was not a system of equations, if it was only this, only the dot product, then we could have two solutions. But we also said that an times bm as a polynomial product is 6, 7, 1. Subscript 14. Remember, for the polynomial product, we know that n times m of the two sectoral structures will give us the degree of the result. So therefore, we know that the degree of AN and BM must have a product of 14. So it will either be 1 times 14 or it will be 2 times 7. And if we go back here, we know that we had 6 1 times 1 1. 6 1 it has a degree of 7 and 1 1 has a degree of 2. 7 times 2 is 14. So we already know that this will be the correct answer. However, to be thorough, we'll turn this into a polynomial form and we will say 6x squared plus 7x plus 1. And we will try to see a factorization that matches one of these results, and it's clearly 6x plus 1 times x plus 1. We convert these to sectoral form and we get an is 6 1 subscript 7 and bm is 1 squared subscript 2. Now let's use the concept of conjugates and apply some of these to it, and we will now start to see some very unique ways of using these operations. So an dot the conjugate of an gives us 232 subscript 7. So since this is a dot product, that means that both an and its conjugate must have an order of 3, which is not very common when we see the a sectoral structure and its conjugate having the same order, but it does happen. So therefore we will say that an must be homogeneous to the conjugate of an. So let's say an is equal to abc subscript n. Then its conjugate, and you can go back and see how we calculate the conjugate. Remember, the conjugate of a sectoral structure is another sectoral structure of the same degree, not necessarily the order, where each alpha joint is converted to a beta and each beta to an alpha. So the conjugate of ABC will be 1 to the power of a minus 1, 2, 1 to the power of b minus 2, 2, 1 to the power of c minus 1. So you can see here that the order of the conjugate is, if it looks like that, it's usually going to be much larger than the order of this sectoral structure. So where if you look at it just initially, like this has to be at least, this will have an order greater than 5, but we want the order to be 3. So what can we do so that the order of this conjugate is 3? Well, we have 1 to the power of a minus 1. So 1 to the power of a minus 1. We can try to get rid of this term. If a minus 1 is equal to 0, then 1 to the power of 0 means that there are no terms, like it cancels this entire chain. So a minus 1 equals 0, therefore a must be equal to 1. So we've cancelled this term. Similarly, we can cancel this final term here, 1 to the c minus 1, if we say c minus 1 equals 0, therefore c equals 1. So we've cancelled 2 terms. So therefore, we can substitute for a and c, we can substitute 1. So an will be 1, b 1. And the conjugate of an will be 2, 1 to the b minus 2, and 2. Now for this an, the conjugate of an, to maintain an order of 3, then b minus 2 must equal to 1. So we can only have one term of degree of weight 1. So b minus 2 must equal to 1, therefore b must equal to 3. So therefore an must equal 131 subscript 5, and the conjugate of an must be 212 subscript 5, and we can double check if that is correct. It's clearly, if we do the dot product, we get the right answer as well. So this is a unique type of algebra